Okay, so let's talk about conditional probability traps or errors that people can make. And they're very subtle errors and sometimes leading to very big mistakes, when you use one probability instead of another. Okay, so conditional probability traps. Okay, and the issues arise because we have so many different kinds of probabilities and the differences between them are very subtle. So imagine you have an event A, so you can compute the probability of A. Okay. Now if you have another piece of new information B, you can compute the probability of A given B. So updated probability of A. But there's what's also, this is the conditional probability. There's also what's called the transposed conditional. So the probability of B given A. And we know that these two are not the same. So one mistake that can happen is that you compute one instead of the other. Okay? And then there's also another kind of probability, which is the AND. So if you have two events A and B, there's the probability of A and B. Okay. So now let me tell you about a couple of, conditional probability traps. The first is what's called sampling bias. Okay, sampling bias. Okay. And mathematically, you're basically using probability of A, so the unconditional probability instead of probability of B. Of A given B. And this often occurs in sampling. So you're doing a medical trial, so you sample some people and try a drug. Okay, and one place where this happens a lot is when we try to sort of estimate, who's going to win an election. Okay, so you can think that all the 250 million voters or 200 million voters or so, that's the sample space. And if you randomly picked a voter, what are the chances that they would vote Republican? So the probability to vote Republican, let's say, is approximately a half, because there's roughly an equal number of Republicans and Democrats, and on any given election, it can go up or down, let's say 0.5% or 1%, okay? So it's approximately a half. But now you want to test this hypothesis. So what you're going to do is you're going to do this experiment. You're going to randomly pick, a voter, ask them, who are you going to vote, and keep doing this. Do this experiment many times. So randomly pick voters and ask. Okay, and you should find that approximately half of the people you picked will say they voted Republican. Okay, but now when you do this experiment, how do you actually implement it? So one thing that we could do is we could ask Apple. So we ask Apple, to send a text message to all iPhone users. Okay, so ask all, because they have control of the iPhones. Let's say iPhone users to say how they vote. Okay, so Apple does this and then comes back to you and you find that the fraction that are voting Republican is very much greater than a half. Okay, and you wonder, wow. So does this mean that the frequency interpretation of the probability is dead? No. And that's because, there's a very subtle new information here, which is, who did you ask? You asked people who had an iPhone. Okay. So we didn't compute the probability that a random voter votes Republican. We have computed in this experiment the probability, or we've approximated the probability that you vote Republican given that you have an iPhone. Okay. That's a very subtle piece of conditioning. It's a subtle piece of new information. And it turns out that this number is much, much greater than a half. And so you'll make this mistake that you'll think that there are way more Republican voters than there actually are, because the way you sampled voters has biased you towards owners of iPhones. Okay, so that's why it's called sampling bias. Okay. And why is this the case? That typically you'll find that Republican voters are a larger fraction than 50% of iPhone owners, because iPhone owners have to be rich. And it tends to be the case in the US that Republicans or people who vote Republican tend to be more pro-business and, wealthier. Okay. For a famous example of this, do a Google search. Okay. On, Dewey defeats Truman. Do a Google search of this. You might be saying, well, what? Dewey? Who is Dewey? Yes, that's exactly the point. Do a Google search on this and you'll see a famous example of this. Okay, I'm going to move on to another example, what's called the fallacy of the transposed conditional. So the transposed conditional. so the transpose conditional is where you're using probability of A given B when perhaps you should be using the probability of B given A. So using one conditional instead of another of the transpose. Okay, so probability of A given B instead of the probability of B given A. Okay, a famous example of this happened in a study by Lombard, where Lombard wanted to figure out what's the riskiest profession. Okay, so because he had no other way to sort of investigate the riskiness of professions, he went to the morgue, okay, and he surveyed death records. And upon death, he looked at what was your profession. So profession upon death. Okay. And then he also looked at what was your age, so that would tell him about your lifespan. Profession upon death, and also age. And you want to know what the riskiest profession is? Student. Riskiest profession is student. Oh, don't worry. Don't quit. Okay, don't quit yet. Okay. There's a flaw in Lombard's paper, which is he's looking at the transposed conditional instead of the correct conditional. So let's see what he actually did. What he actually did was, okay, so he took all the people who died, let's say, younger than 20. Okay. And then he looks at what's your profession. Oh, they're all students. Then all the people who died between 20 to 30, what's your typical profession? Oh, those guys tend to be in the military or what have you. Okay. So what Lombard was actually tabulating was, what's the probability of, a particular profession, okay, given that you died at a certain age. Because what we see in the data is the age at which you died, and then we can look and see what's your profession. So given that you died, let's say, died at less than or equal to 20. Okay. And no surprise, if you died at less than or equal to 20, then, if you give me that as a piece of information, then it's pretty clear that most of those people who died less than or equal to 20 are students, because you haven't had time to do anything else. What Lombard actually wanted, he wanted the probability that you die at age less than or equal to 20, given your profession. So given that you are a student, what are the chances you die at less equal to 20? Okay, so let's change it now, not to 20, but to, let's say, 30 or 40 or 50. Okay, what are the chances you die at less equal to 30? Given you're a student, given you're in the military, given you're a doctor, and so on and so forth. Okay, so this is the correct conditional that he wants, but he measured this one. Okay, and some strange things occurred here. For example, I think the least risky profession was something like, chocolatier or something like that, or morgue operator. Some weird professions. And that's because those professions only come into play. You only become that if you live long enough. So given that you lived long enough, what's your likely profession? And given that you live long enough, it's almost, impossible that your profession will be listed on your death certificate as student, because you would have done something. Okay? So no students lived long. And all people who died young were students. Wrong conditional, transposed conditional. So let's erase. I'll come back and show you another fallacy of the transposed conditional, and we're going to discuss medical testing. Okay, medical testing. So this is an example where, people tend to fall into this trap of the transposed conditional. So they need one conditional, but they use another, and actually it can lead to some panic. Okay, so we have a lame test. You have a test for lame. Okay, so we've created a test for lame, loud and mostly erroneous behavior. Okay, and let me tell you some of the properties of this test. So, if you are lame, it's a pretty accurate test. 10% error rate. Okay, so this is sometimes called, if you're lame, 10% error rate. This is sometimes called the false negative rate. And if you are not lame, So 5% error rate. Okay, so if you're not lame, it says that you're lame 5% of the time. So that's called a false positive rate. Okay, and about 1% of the population is lame. So 1% of population is lame. So you got tested. You were tested and you came up positive. Okay, and now you panic because look at the reasoning. Okay, so, could you be not lame? So, if you're not lame, okay, that means the test is wrong. Okay, and the probability that test is wrong is very small. Okay, because if you're not lame, it has only a 5% error rate. So the chances are very small that the test is wrong. Okay, so, it looks like, therefore, that you must be lame, because if you're not lame, it's a very unlikely situation. This is kind of like a probabilistic proof by contradiction. Let's see what happens if you're not lame, and we come up with something unlikely, and therefore you must be lame. Well, there's no such thing as probabilistic proof by contradiction. There's proof by contradiction, but there's no such thing as probabilistic proof by contradiction. And what's the problem what's going wrong here? Actually, what you're looking at here is the probability that the test is wrong, assuming that you're not lame. And that's where you get that this number is very small, because if you're not lame, the test is very accurate. But, this probability is of no use to you because you don't have the information that you're not lame. So you cannot compute a probability conditioned on being not lame. The information you have is that you tested positive. So the probability that you need to look at is the probability that you are not lame, given that the test is positive. Okay, because this is the information you're given, and this is what you would like to know. You'd like to compute the probability of being not lame. Now, if you didn't have the test, the probability of being not lame is 99%, because 1% of the population is lame. But now that you have the test, let's see what's the probability that you are not lame. We can just, blindly use a mechanical approach to computing conditional probability. So let's do the experiment. The experiment starts with you. Okay, so you can either be lame, or you can be not lame. Okay, and now you're going to get the test. In either case, the test can either say yes or no. Yes or no. Okay, and in this case, you're lame, and the test said yes. In this case, you're lame, and the test said no. In this case, you're not lame, and the test said yes. And in this case, you're not lame, and the test said no. So there are 4 outcomes of this experiment where we decide whether or not you are lame and then what the test says. Okay, now the chances you are lame is just 1 over 100, 1%. The chances you're not lame, 99 over 100. Okay, and the chances that, okay, now if you are lame, in this situation, the test gets it wrong, with the chance the test gets it wrong is 10%. So it's going to say no, chances are 10 over 100. Okay, 10%. And the chances that it says yes are 90 over 100. Okay, it's right 90% of the time. And here, the chance that the test gets it wrong, so says yes when you're not lame, is only 5 over 100. And the chance that it says no is 95 over 100. So we can compute the probabilities. Okay, so the probabilities are, multiply 90 times 1 over 10,000 over 100 times 100. So 90 times 1 over, so that's 90 over 10,000. Here we have 10 over 10,000. Here we have 5 times 99 over 10,000. And here we have 95 times 99 over 10,000. Okay, so if you do this experiment with overwhelmingly high probability, the chances are overwhelmingly high that the outcome is not lame and no. But that's not what happened. Okay, what happened is that the test said yes. So one of these things is what happened. Okay, but let's just continue. Let's compute mechanically the probability that we want. So the probability of not lame given yes, okay, is equal to the probability of not lame and yes divided by the probability of yes. That's just the formula for the conditional probability. Now we need to compute those individual regular probabilities. The probability of not lame and yes. So not lame and yes is just one outcome. 5 times 99 over 10,000. So this is 5 times 99 over 10,000. divided by the probability that the test says yes. So what's the event where the test says yes? This outcome and that outcome. So the sum of those outcome probabilities gives us the event probabilities. So the probability of yes is the sum of these two. So 90 over 10,000 plus 5 times 99 over 10,000. Okay, so these cancel out. So this is 5 times 99 over 90 plus 5 times 99. And if you compute this, it's approximately equal to 85%. Wow! Okay, so let's now interpret. There's a rare disease, Lane. Okay, you took the test for it. So it's rare because only 1% of the population have it. You took the test for it, and it's a pretty accurate test. Okay, and you came up positive. And still, the chances that you are not lame, even though you came up positive, are 85%. It's way more likely than not that you are not lame. Let's see what's going on here. Okay, what's going on here is when the test says yes, okay, one of two things happen. Either you are lame, which is rare, and the test got it right, which is what the test normally does. That's often. Or you are not lame, which is often, and the test got it wrong. So the test is correct, that's often. And the test is wrong, that's rare. Okay? So let's see what's going on. Here, you have the choice of a rare thing followed by a normal thing. And here you have a choice of a normal thing, often thing, followed by a rare thing. Okay? And so there's sort of a balancing between rare and often whenever the test says yes. And in this case, option 2 wins. That it's more likely that the often not lame thing wins, combined with the test being wrong. Okay. And what's going on here? What's going on here is that the background population, the fact that 99% of the people are basically not lame, is overwhelming the test. Okay. And that results in, it's way more likely than not, even though the test says you're positive, it's way more likely than not that you are negative. And this is the situation that's going to happen with any very rare condition. Okay. So most tests for these rare conditions, they're not 100%, so they're pretty accurate, something like this. Okay, maybe slightly more accurate. But, once you have a very rare condition, even when the test says positive, chances are you don't have it. So then what's the use of the test? Okay, well, here's something that you need to know now. For rare conditions, when the test says yes, what should you do? Okay, what you should do is you should ask to be retested. Okay? Because this experiment, so now the experiment continues. Okay, so if it says yes, you try again. And if it says yes again, now you see you're compounding the chances that the test is correct versus the test saying yes, and you're not lame is getting rarer and rarer, and now you're getting a more and more accurate test. Effectively, you are trying to boost the accuracy of the test by repeating. So if it's a rare condition and you test positive, you better get retested before you panic, okay? Because this is what's going on. This is what the conditional probability says. Okay, so now let's erase and we'll back and we'll talk about the law of total probability.